For our third shuffle today, it's also a transposition, but I call it a judicious transposition. That's why I have the letter J. J is standing in for the word judicious, which means wisely chosen or wisely determined. Now, the first two shuffles today, we did a stacking from left to right, and then we did a stacking from right to left. Here we're going to do a more complicated stacking. It's also referred to as a leapfrog stacking, as you will see. So I begin with the ordered packet 1 through 8 and perform the shuffle. So it begins the same. I go 1, 2, 1, 2, 1, 2, 1, 2. And now the stacking is as follows. Pile 1 gets stacked on top of pile 3. And I've referred to this as a leapfrog stacking. It's leaping over its neighbor. Now pile 2 gets stacked on top of pile 4. So you can think of that as a leapfrog action. So it's leaping over that one. And to finish, we're going to stack the left pile on top of the right. So left on right. Okay, so what is the new order that results from this shuffle? Well, let's take a look. It looks like it's 2, 1, 6, 5, 4, 3, 8, 7. So in Cauchy's two-line notation, we get the following. We get 2, 1, 6, 5, 4, 3, 8, 7 as the bottom row of our two-line notation. Converting that to cycle notation, we obtain the following. 1 goes to 2, so I have an arrow from 1 to 2. 2 goes to 1, so 2 cycles back around to 1. So we get a 2 cycle, or in other words, a transposition. 3 goes to 6, and 6 returns to 3. So we get a second transposition. 4 goes to 5, so I have an arrow from 4 to 5. And then 5 goes to 4, so it cycles back around, completing that 2 cycle, which is also called a transposition. Finally, 7 goes to 8, so I have an arrow from 7 to 8, and then 8 goes to 7, so it wraps around. So that completes our fourth 2 cycle, or in other words, our fourth transposition. Color coding the digits, we obtain the following. Recall that the color coding of the digits is as follows. Positions 1, 4, 6, 7 have been color coded black. Positions 2, 3, 5, 8 have been color coded red. This will help us keep track of whether cards in these positions stay within those positions, or is there a wholesale replacement with the cards in these positions here, 2, 3, 5, 8. If there is, we say that an inversion has occurred, and we represent it like this. If no inversion occurs, then of course it's represented like this. So we see that black 1 goes to red 2, which cycles around to black 1. Red 3 goes to black 6, which cycles around to red 3. Black 4 goes to red 5, which cycles around to black 4. Black to red 8, which cycles around to black 7. So we see here that each value gets sent to a value of the opposite color. And when that happens, inversion has occurred. So why don't we go ahead and illustrate that inversion does indeed occur. Here is our quintessential Bessey sequence. So if we perform this shuffle on this labeling of the cards, we obtain the following. So here you do a 1, 2, 1, 2, 1, 2, 1, 2. That's always the same for a transposition. Now the stacking is different. We're going to stack 1 on top of 3, 2 on top of 4, and then the left pile on top of the right. So what we should get is the inversion of the Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, and the inversion is 0, 1, 1, 0. 1, 0, 0, 1. So an inversion has indeed occurred. Taking a look at the graph for this shuffle, we see the following. That there's a double arrow between 1 and 2, a double arrow between 3 and 6, a double arrow between 4 down here, which is kind of hiding, sorry about that, to 5, and then a double arrow from 7 to 8. And as we'll see, there is no other shuffle that we have or will present in this series that has that identical shuffle diagram. So in that way, it is unique among the shuffles we will present in this series.